Hi, this is Kevin from the Mathsaurus, and in this video we're going to look at solving separable differential equations. And these are incredibly important types of differential equations, and they come up in a lot of different contexts, so you might be studying this on all sorts of degree courses in sciences and things, but in particular they are the only type of differential equations that we need to know about for A-level maths. So if you watch this video, you should be able to solve all the things that come up in A-level maths. So we'll go through 4 stages. We'll talk about differential equations a little bit in general. We will talk about a problem of exponential growth, a differential equation that models how population sizes grows, how diseases grow, also used in physics for things like half-lives, all sorts of applications here. That's an example of a more general type of differential equation called a separable differential equation. So we'll look at the theory of that in general, and then we'll do a harder example of exactly the sort that we might get at an A-level maths exam. So differential equations in general. Okay, so what is a differential equation? It's just an equation that involves the derivative dy by dx, or perhaps some higher order derivatives as well. So for example, these are all differential equations. You know, dy by dx equals 3x squared, dy by dx equals 3 times y, dy by dx equals e to the x times y squared, x squared dy by dx is y squared minus 4y plus 3, or dy by dx squared plus 3xy equals 2y cubed minus d2y by dx squared. These are all differential equations, right? Anything that's just got terms with x and y and dy by dx, or higher derivatives. So in this video we're just going to look at the first, I said 3 here, actually the first 4 of these differential equations we'll be able to solve. The last one is suddenly super hard, right? So actually solving differential equations in general is just super hard, right? There's no single method that says this is how you solve all differential equations. So we just find certain types of differential equations that we know how to deal with. So almost certainly, in fact, this first differential equation is something you know how to solve already, and we'll look at that in a second. But the basic thing to bear in mind here is that the rules for manipulating differential equations, they're just the same as for ordinary equations, right? So, you know, if we've got a differential equation and we perform an operation to one side of the equation, multiplying it by 5 or something, we also multiply the other side by 5. Okay, but the slightly different thing we get out of a differential equation is that the solution is going to be a function of x rather than just a number when we solve an ordinary equation. Okay, so the solution might look like, you know, y equals x to the power of 5 minus sine of x or something. And very often when we solve differential equations, the thing we do to each side is integrating it, right, or something, you know. So they can feel a bit different, but basically their rules are the same as usual. So that first differential equation on the list, dy by dx equals 3x squared, what's this saying? It's just saying, can we find a function that when we differentiate it gives 3x squared? So really, you know, you've come across this problem in integration already. So if I wrote this down slightly formally, I would say if I integrate the left-hand side with respect to x and the right-hand side with respect to x, I would get this, and then, you know, the integral of the derivative is just the original function, so this becomes just y, and we know how to integrate 3x squared, we get x cubed plus c. So in general, you know, the solution here, this general solution, is a function of x, and actually it's a whole family of functions of x, right? So, you know, any different value of c, for any different value of c, this x cubed plus c function differentiates to give 3x squared. Sometimes people ask me at this point, why don't we put a plus c on both sides of the equation? And the reason is that c here is an arbitrary constant. So imagine I had, you know, y plus d equals x cubed plus c. Well, I could just subtract the d and have y equals x cubed plus c minus d, and, you know, if c and d are totally arbitrary, then c minus d is just as arbitrary. So, you know, in some problems, as you'll see, we'll work out what that constant is, and having 2 constants is a waste of time. So you will see how that happens later. Right. You know, so in particular, you know, sometimes this differential equation comes with like a boundary condition. So same differential equation here, but this time we're going to say y of 2 is equal to 10. Right? That just means that when x equals 2, y equals 10. So we get the same solution in general as before, y equals x cubed plus c, and now we substitute in the boundary condition, x equals 2 when y equals 10, and we find that c equals 2. So the particular solution there is just y equals x cubed plus 2. Okay, so an easy one to start with, but it really sets the tone to understand the harder stuff. So the next thing we'll talk about is exponential growth, right? And this particular type of differential equation. So the second differential equation was dy by dx equals 3 times y. So rather than having a function of x on the right hand side, I've now got a y, right? And this is really a useful differential equation. For example, if we think about the variables as n and t, so maybe the number of people in a population or number of animals in a population, and t is the time, what this sort of thing says is the rate of change of the population with respect to time is proportional to the current size of the population n, right? So as n gets larger, so does the gradient dn by dt, and this makes a lot of sense, right? For example, for modelling the outbreak of a disease, the more people that currently have the disease, the more new infections there will be. So as there are more people with the disease, the rate of increase also goes up proportionally. So let's look at this particular example, dy by dx equals 3 times x. And so if we integrate both sides this time, we get, again, the integral of dy by dx equals the integral of 3y dx, or y equals the integral of 3y dx. Now, this isn't helpful. All this has done is just rephrased the differential equation as an integral equation. But the fundamental problem here is that I've got an integral with respect to x, but the thing in it is a y, right? So I could do an integral of y with respect to y, I can do an integral of x with respect to x, but those variables have to match up. And it's at this point in calculus that you really start to realize why, when you do integration early on, your teachers might be, forcing you to write dx all the time, even though the variable is always x and it doesn't seem to matter. It starts to matter here. So let's do something different. Okay, that strategy didn't help us solve it, but if instead we were to divide both sides by the y, before we integrate, we'd get 1 over y times dy by dx is equal to 3. And now if I integrate both sides of that equation, I get 1 over y times dy by dx is the integral of 3 dx. The right-hand integral, super easy. And if you think about the left-hand integral here, we can actually cancel out the dx's here, and this is the integral of 1 over y dy. Now this is kind of a subtle result, but it's exactly the sort of thing you do when you do integration by substitution. So all I want to say here is that there's some kind of chain rule integration by substitution kind of effect going on here. If you think about these as small increments of x and y, then this will be very natural and make a lot of sense. But when we have this, the integral of 1 over y dy dx, we can write that as 1 over y dy. And you see now we can do both of these integrals. We can integrate both sides and continue to the solution, right? So integrating 1 over y, hopefully you know that gives you log of y. Again, some students would pause me here and say, hang on, isn't it log of mod y? And I would say, yes, it is. And we might also write log of mod y here. In this example, I'm just assuming that the variables we're dealing with are positive, like you'd have in an exponential growth model here with positive time and positive numbers of people, but in some situations you might want to put a modulus here. And the right hand side, we integrate the 3 and we get 3x plus c. And so if I take e to the power of both sides, I get y is equal to e to the 3x plus c. And again, we get this exponential result. Now, very often, this differential equation we write as slightly differently to this, right? So we think of the e to the 3x plus c as e to the 3x times e to the c. And instead of writing e to the c, we write capital A. Okay, and then we've got this nice form of this equation, right? So again, c here is just an arbitrary constant, and so a here is also just an arbitrary constant. It has to be positive, but otherwise, it can take any value here. And that's quite a nice way of writing things down, because in this more general case, where we've got dn by dt is equal to k times n, right? Exactly the same argument would tell us that the solution is n equals a times e to the k times t. And then this a can be thought of as the number of individuals in the population at time t equals 0. Because if you put in t equals 0 here, you just get n equals a times e to the 0, and e to the 0 is 1. So you often see this written like n equals n0 e to the k times t, right, where n0 is the constant, that's the starting value. Right, okay, so what are separable differential equations then? Actually, what we've just looked at is an example of a separable differential equation. And in general, a differential equation can be called separable if you can write it as dy by dx is some function of x times a function of y. And we're going to apply the same sort of idea as we had above. Okay, so if this general form looks a bit confusing, don't worry, there'll be an example very soon. And in this case, then we can write this as 1 over g of y times dy by dx equals f of x. Then we can integrate both sides with respect to x, as we did before. The right-hand side is a function of x with respect to x, so that's great. And again, by the same argument as before, the left-hand side here, we can simplify the dy dx to dy, and I've got 1 over a function of y, which is also a function of y dy. Right, so you see in principle this strategy can work if I can get all the y's on one side, all the x's on the other side, and then integrate. And then the question is, do we know how to integrate each of the things we've got? And that will depend on the functions f and g, but at least we've got a chance. So here's an example. Suppose we want to solve dy by dx is equal to e to the x times y squared. Well, we do exactly what we've just laid out in our plan, and we divide by y squared, and then we integrate both sides. And so we get the integral of 1 over y squared dy is equal to the integral of e to the x dx. And fortunately here, these are both integrals we know how to do. 1 over y squared integrates to minus 1 over y, and e to the x integrates to e to the x. And we put a constant of integration in here for good measure. So you could, if you want to, write this as taking the reciprocal of both sides and negating y equals 1 over minus e to the x minus c. And just notice here that it's slightly different sometimes in these differential equations. We're used to having the plus c just as a plus c, like separately like this. But it does matter here that the minus c here is on the bottom of this fraction, right? The constant of integration comes when you integrate, so you can't just like get your solution and then plug a plus c at the end, right? The c has to be in the fraction here. But we can rename it if we want, right? So c is just an arbitrary constant we haven't worked out yet. So if we call capital A minus c, then you could write this as 1 over a minus e to the x for a slightly nicer form. Right, and again, if we have a particular boundary condition, then we can work out the value of a, and you see the reason we can do this renaming is because working out the value of a here is no different than plugging in the boundary condition and working out the value of c, right? Okay, we'd get minus, a would come out to be minus whatever c would come out to, but then ultimately the form of the function would be the same. So, as an example, if x equals 0 and y equals 1, you can plug in x equals 0 here, e to the 0 is 1, so we get a minus 1 is 1, and a equals 2, and our particular solution for this equation would be y equals 1 divided by 2 minus e to the x. Okay, so here's a harder example, and this is exactly the sort of thing that can come up in the A-level exams. And here we've got a differential equation, x squared times dy by dx equals y squared minus 4y plus 3. By the way, this example is harder, not because we're going to do anything different with the actual method of separable equations, but just because the actual integrals and the rearranging is harder. Okay, so this isn't quite in the form of a separable differential equation, but clearly, it's equivalent to that, right? Dy by dx is a function of y times a function of x. That function of x here would be 1 over x squared, because, if I just divided through by x squared. But actually, we want to, and actually we're going to do that. We're going to divide through by the x squared here, and also divide through by the y squared minus 4y plus 3, and we get exactly this form here. And then we integrate both sides of the equation, so we've got our function of y with respect to y integrated is the integral of this function of x with respect to x. And so we can carry on as long as we know how to compute these integrals. So the hard part of this question is doing this integral, 1 over y squared minus 4y plus 3, and you're expected at A-level just to be able to know that you do this by factorizing the quadratic here, 1 over y minus 1 times y minus 3, and use the method of partial fractions. So if you don't know how to do partial fractions, I'm not going to go through that in this video. Do look that up elsewhere. But by that method, we can write this integral as two fractions here with linear denominators. So this one, if you do the numbers, it works out as 1 over 2 times y minus 3 minus 1 over 2 times y minus 1, and you can check that if you like. And that means that this integral that we've got here can just be rewritten as, if I pull the half out of each of these fractions, I've got a half times 1 over y minus 3 minus 1 over y minus 1. And then, again, basic chain rule integration here. I don't want to talk about that method too much in this video. I'm hoping doing this subtopic you already know how to do that, but look it up if you don't. This gives you log of y minus 3 minus log of y minus 1. And again, you know, depending on positivity and things, you might just think about whether you want to put a modulus here instead of the brackets, but let's just assume everything's positive here. So we get that, right? Okay, so we can do both the integrals. Right, we can do this. Oh, and there's no constant. You know, as a question on its own here, there'd be a plus c, of course, but we'll just put that in the differential equation here. So we can do that first integral, and the other one is easy. It's just x to the minus 2, so I get minus x to the minus 1, or minus 1 over x, and there's our constant of integration. Right, so in a sense we've solved the differential equation, right? This is a solution. But sometimes we also want to try and make y the subject here. And again, you can be asked to do that. So here we would use the rules of logarithms to combine log y minus 3 minus log of y minus 1. That's just a log of the fraction y minus 3 divided by y minus 1. And then when you put a half outside, then that becomes a square root inside the logarithm, because it's the half power, so that's log of the square root of y minus 3 divided by y minus 1. And on the right hand side, minus 1 over x plus c. So we can do e to the power of each side of the equation, like so. And again, the c is in the exponent here, so we could rewrite that as we did before, thinking of this as e to the minus 1 over x times e to the c, and just replace it with a constant a. And again, this is also a perfectly good form. As I'm saying here, we could make y the subject, and then to do that we could just square both sides of the equation. And again, you know, when we do this sort of stuff, we often do a bit of renaming of constants, right? Because so I square both sides here, and what do I get? I get a squared times e to the minus 1 over x all squared. So by the rules of powers, that's just e to the minus 2 over x. And let's just call a squared b, so I don't have to keep writing a squared. It's an arbitrary constant, so still an arbitrary constant. And now we've just got an equation where y appears twice, so I can make it the subject by multiplying by y minus 1, by multiplying out the brackets, and so you can see what I've done here, right? I've multiplied out the brackets and gathered together the terms in y, right? So this minus 1 here is not this minus 1, this comes from the y over here, right? So if you multiply it out, you get b to the minus 2 over x times y minus this y here, and factorize it, and then I would get the b to the minus 2x times minus 1 here, that appears on this side, minus 3, right? So check the algebra if you need to. And then we can divide through by this bracket, and we finally get the solution with y being the subject. So you can see this is a great A-level question for 8 or 9 marks or something, because you can do the method of separable equations, you can do a tough integral, and it's also testing your fluency in the rules of logarithms and seeing your way through a tougher algebra problem as well. And they do sometimes ask a little bit about interpreting these solutions as well, like what happens as x gets very large here or something like that, and you can think about those questions as well. In fact, at some point I'll do a video with some exam questions in, and we'll go through some more of those as well. So I hope that was useful. Now you know how to solve separable differential equations, and these are super useful. Differential equations, there's so much you can learn about differential equations. As I say, in general, a very, very hard problem to solve them, but there's lots of particular types of differential equations that we can solve nicely, and this is really the first of those types. So I hope it was useful. Please do like the video and subscribe to the channel, and share this with your friends if it was. let me know in the comments if you've got any questions or if there's anything else you'd like to see.